So, well, based off of these probabilities, zero probabilities, we can also calculate like how much risk we would have to make a mistake. We had previously noted that the error would be like 1 minus the maximum of the two probabilities, and so we're like, if you have like 0.7, you would have like 0.3 as a mistake, or the interesting part here is to be able to compute this risk, and as you can see here, like we have this lambda ik parameter, which basically means that if we choose the class I, what is the loss, or like the penalty that we would get if it actually would have been class K, right? The special case, we're going to come to that in a second, is obviously like you would have like a 0-1 loss, so you would always count every error the same way, but sometimes you just have like different in a different classification problem, it might be more costly to make one mistake over the other, right? So yeah, so basically it's defined as like, this is basically the loss parameter, the loss weight of taking an action when the class is actually class K. Yeah, so if you want to use these risks as your classification rule, you basically just choose the minimum risk, okay? So that is influenced, so is really strongly influenced by the risk of making a certain type of mistake. So if you choose these parameters like accordingly, you could, for example, reject that spam message with 0.96 probability if you just had a very large lambda parameter for the class of like rejecting an important message over that. Okay, so you might need 0.99 as a probability for spam, so that you're not like throwing away important messages or something like that. Okay, so you can tune these parameters accordingly, and depending on a type of experiment you're running, the type of data you have. Okay, so that's kind of like the idea behind that. We had the special case, which basically means this is chosen to be 0 if we don't make a mistake, and 1 if it's actually a mistake. And basically, the risk of taking an action then is just 1 minus the probability. Okay, and then it becomes the same kind of classification problem. So, thus to minimize the risk, we choose the most probable case if we have like the 0-1 loss. Depending on the parameters in the other loss calculation, we would have the ability to choose a different class. Another special case here would be to reject certain inputs to the classifier. So that would be, for example, the case if it is more costly to make a wrong decision over making no decision. So if your classifier is really not certain over both, it might be better to ask a human user, like, hey, what do you think about this? Or it might just be better to just say, like, I don't know, right? So the classifiers could theoretically reject the case, or just say, like, I don't know, and basically what we need to do to allow this and to fit it back into the previous example is we just allow another action, which is the I don't know action, and the possible function would then just look like this. So where we would output lambda if I equals k plus 1. And so the risk to reject in that case is just that lambda parameter, if we bring that into the 0-1 loss. The decision rule in this case would just be choose action alpha I if it's smaller than the risk of all the other classes, and if alpha is also smaller than the risk of taking no action. Okay, and we would reject if this does not hold true. That second part. And then, yeah. So, what is this for? Or we choose, yeah, because we just put that parameter in there. Okay? All right. Any questions today? And so this is just like, we're probably not going to use reject in experiments and homeworks, but just so you know that it exists, and that depending on the task, it might really be a lot safer to not say anything, to not make a decision over making a wrong decision. Okay? All right. So then we can continue to nonparametric methods. And so nonparametric methods, there are like actually a bunch of those. We're going to talk, I think maybe next week or this Wednesday, we're going to talk about decision trees as well, which are also a nonparametric method. But today, I think we're going to reduce ourselves to some like basic classification experiments and nonparametric density estimation, which are, for example, like nearest neighbor classifiers. All right. So, when do you use nonparametric methods? You use them if you don't really know anything about your data. So you have zero assumptions about the data, and you don't know if they're like normally distributed, or you don't have a good feel for what's going on. And the only assumption that we can make in these cases is that similar inputs have similar outputs. So it's kind of like the world is smooth, okay? So an obvious classifier or an obvious candidate for classification like this would obviously be a k-nearest neighbor classifier. So if I have my sample set and I have a new observation and I don't know anything, I'll just choose the class for the one item or for the k items that are closest to this new item, okay? And then I possibly would enter this new item into my data set, for example, okay? So the closer I am to others, the more certain I am, again, so that, and so like k-nearest neighbor also only works if you like actually sample from the same kind of distribution. So imagine if you have here like a very dense observations, and you in the end like observe something out here. To calculate the nearest neighbors, well, you'll find some nearest neighbors, but it might not make any sense, right? Like the distance is very large, but you would still be able to find the nearest neighbors. So these methods are not really able to like reject those cases and say like, well, this is way far out. You can implement that into your method, obviously, but from the standard evaluations, that's not really happening. Well, basically, now all we can do is kind of find similar past instances or like our training data set and use a suitable distance measure and interpolate between them to find the right output. So we like, okay, what are suitable distance measures? Well, that also depends. Like often we just like use Euclidean distance, but then we also discussed last week that if we don't normalize our data, these methods or these distances might be dominated by one dimension over the other, and so we just want to make sure that the distance metrics that we use are meaningful, okay? But most of the time we would use Euclidean distance. That's just like very easy to write, and but you're not restricted to that. You can use more complex ones. And the interesting part actually is that the complexity of our model is entirely defined by the training set. So you can imagine this like this. So if you, for example, have a clustering problem, so you have many data points, and you start to cluster those data points, and you like identify, okay, this is one centroid for this cluster, this is another centroid for this cluster, this is another centroid for that cluster, right? So you have now approximated your data set with 3 centroids. And these could be like the 3 prototypes, your code book, so to say. And once you observe something new, you choose which prototype is closest to like the new data point, right? And you would say, oh, that it falls into that class, or it falls into that cluster. So you only have to look at 3 data points. But in non-parametric methods, you always have to look at every data point. So these are really like lazy classifiers. Like all the data points are part of the process of deciding like what class it is, or what how the density looks like. Okay, so that's important. Yeah, so the model complexity is entirely dependent on the training set, and then you can use non-parametric approaches to use like estimation density, estimate the density functions. So you could, for example, like visualize where your data set is dense and what regions, where it's sparse, and then you can do classification with k nearest neighbor if you have a label associated with that, and you can do regression as well. I'm not going to cover that today, but you'll see basically immediately how that could look like in one of the visualizations, and I'm going to point it out. Okay, so these non-parametric methods also are like part of the instance-based learning methods, where you basically treat your entire data set as a lookup table. So I have a set of observations, and I get a new one, and I just choose the one that it's closest to, right? So you have to, every single time I get a new observation, I just have to go through the entire data set and check which one's closest. So that's a computation requirement of O of the number of observations in my data set, where I need to store it too, so it's O of n. And you can already see, well, this is kind of like, there's no training involved in this, right? Like, I always just do readouts. And so, like, this is why they're called lazy classifiers, because you never do any training beforehand. You always do, like, all the computation at the readout. But any other method that we're going to cover in the course does training beforehand, might be actually computationally expensive, but in the end it's like a comparison with a lot fewer items, or it's running like your input through a neural network, which requires a couple of matrix multiplications, and you're done, right? But there's not much computational effort after you have trained the model, okay? But these methods don't train previously, and so they have to do all the work at a later stage. And yeah, the contrast, the other methods are the eager methods that basically do all the work beforehand, and at the end they don't do anything anymore, except for reading out the input. All right. So we can, for example, now do non-parametric density estimation with our sample. So we have like n many observations. They might be n-dimensional, whatever, but we can compute a distribution and the density for this random variable x by just doing the following, where we basically have our density here, and we count the number of times items here fall into a region of plus or minus h, which could be like a variance, like a variable term, minus the items that fall. So like this is basically on a line. So like the items that are like past a certain level or below a certain level, okay? And then we divide that by the number of observations and normalize it by the width of this kind of like close enough parameter. It can be like it defines a neighborhood, okay? So in this case, like the h denotes the interval that is considered to be close enough without specifying the distance measure, and then all the others are kind of like too far away. And the techniques that we show afterwards are basically just modifications of this simple approach that is just relying on counting. And so the first one that we could look at, for example, is if we choose h equals 2, which is basically we allow it to be 2 wide. So we count how many items are between here and 2. And then we just say, okay, it's 1, 2, 3, 4. And then we divide that by the total number of observations, and we get like a histogram for this data set. So we have only 1 here, so this is then that, and like we have 3 up here, and no observations in here. So that doesn't get any support there. So this is like how you can visualize like the density of your data set through histograms. If you now modify this h parameter to, for example, 1, then you get like finer bins, okay? And so now this one, for example, wouldn't be getting any support anymore, right? Mm-hmm. And then the further, the more fine-grained you do this, the more fine-grained and jumpy your function becomes, okay? So this is basically just very, very simple histograms, right? Like if you plot a histogram with different width, you're exactly using that kind of rules. So you just look at how many observations do I have in my in these bins that I'm defining, and then you just basically normalize it. In an actual histogram, you would have like the number of observations here, so it would be 1 for this one, it would be 2 for that one, and 1 for the others. So like, and here you just normalize it to actually have a probability density function, okay? So that the sum overall is 1, okay? So if you compute the integral of this. So, and this works like with many different approaches, and so like this one, for example, the INF estimator works similar as a histogram estimator, and however now we don't have like a fixed interval, but every bin, so to say, or every histogram bin is centered around each point. So like these curves can be more interesting. And again, you have this h parameter, and the finer you take it, the more fine-grained these changes are. Okay. So what do we do here? Again, we have our normalization. We sum up over all our data points, and we have this w here, which we'll get to in a second. But we calculate a distance between the x value that we want to know about. Like we move this through here, and minus all the xt's divided by h, and then we have this if 1. This is 1 if we are within a small distance, and 0 otherwise. Okay. So if we fall into the range that we want, and we define that, this will be smaller or equal than a half, right? And we need to use the absolute value because we either can be on the right or the left side of the point, okay? And so again, you can make these kind of interesting probability estimation approaches like that. Okay. But again, like these look very weird, and like usually you wouldn't really want that kind of fine grain where you have these weird outliers. I think you would probably want something more like that. So this h parameter needs to be tuned as well. If you want to have this a bit smoother than what we had before, so you don't want these discontinuities. You can use, for example, a kernel. So instead of this weight function here, you just use a kernel, and a kernel in this sense is just another function that you apply to your distance. So in this case, this is like an RBF kernel, a radial basis function. So it's basically a Gaussian that goes wider and narrower. And you should I think you will see this function many times. It's a Gaussian kernel or a radial basis function kernel. And instead of your W, you just apply the kernel here, which then forces your observations to become a lot more smooth. Okay, so this is kind of like a nice way to estimate your probability density, and this method is also called the Parson window estimator for your probability density. Okay. All right. And now we can move a step further and say, well, what happens if we want to define this just through the nearest observations? So instead of looking at all the items that are close by or within a certain window, we just look at the nearest one, and that basically becomes the k nearest ones. That becomes the k nearest neighbor estimator, and that k parameter can be adjusted in the same way as previously the h parameter was adjusted. So now you're not defining your neighborhood through a distance, but you're defining your neighborhood through the number of neighbors. And so the closer these neighbors are, the more narrow at this location your h window will be. And if they're further apart, that h is actually wider, so to say. So it dynamically changes with the density of your data set. Okay? That's something you can see here, basically, where a lot of observations are close to each other, so you get a lot of support here, and when they're further apart, you get like a flat location. And then if you reduce this down to k equals 1, you only count them here, where you have the observations, and you basically force it down wherever you don't have any observations. Okay? So this is just counting where do you have neighbors. All right? And you can also use this for classification, obviously. And so when we're using the non-parametric approach for classification, we now kind of compute the conditional density. So we want to know the density for the observations x given a certain class, and we just choose the one that has the highest density at that location. So this is with the nearest neighbor classifier, where we have these, we define a k again, that could be 1, 3, 5 nearest neighbors, and you would choose the one that has the highest density. So you would make those, you make one of these curves for each class, and then so if this is class 1, and the item falls in here, you would say, okay, you have a support of 0.9 here, and for class 2 you would have a curve that's down here, so you would have a support for or a density of 0.1 for class 2, so you would choose the one that's higher, right? And to be able to compute this for each class separately, you have this indicator variable that just switches off this computation for if that class is not, if the item is not part of one class versus the other. And this is just a complicated way to like describe how a nearest neighbor classifier really works, and a nearest neighbor classifier is just you have like a cloud of observations, your new data point comes in, and you just look up the 5 or the 3 nearest items, and you count how many of those are part of class 1 and how many of those are part of class 2. You choose the one that are more part of class 1 or 2. So if you have more neighbors that are class 1, so 3 versus 2, for example, you would say class 1 and dismiss class 2. Okay? So that's just a complicated way to do that. So for example, k-nearest neighbor, you would just get a new data point, you calculate the distance to all data points, you choose the k ones that are minimal, and that's how you identify like the class. All right. There's a method to actually condense k-nearest neighbor, because if you imagine like you have many items in your data set, and you would like have to every single time compute the distances to like hundreds of thousands of data points, that might actually become very computationally intensive. You can reduce this if you start to kind of like tessellate your data set into these Voronoi cells, where like every point that lands in here would always be classified as a black class, versus every data point that falls in here would be classified as a white class. So you can start to thin out your data set, like following this algorithm down here. But that doesn't really make a huge difference.
Which means when you have a new data point, you will not redesign the Voronoi for that particular cell, you will just assign it. So this is a training set that will produce a Voronoi.
Yeah, so you don't, I mean, you could start to add your new data points to the data set, but and sometimes like, you have a risk that they might not be accurate, and so on. So, yeah.
So basically do it once for the training set, you get the Voronoi type of a structuralization or whatever, some sort of structure, and then you just check.
Yeah. Oh, it's just
so is it still non-parametric?
Yeah, I mean, it's not lazy anymore.
It's not lazy anymore.
Yeah. Okay. Yeah, we're kind of done with today's lecture. Let me check.
Noise and stuff. That's what we do here.
The next one will be. Yeah, so I think we might be able to go through this at least a little bit. I have to kind of leave a little early today because I have a doctor's appointment, and I don't want to miss that because it's for my green card. Who knows what's happening?
Don't leave the country.
Yeah, it will be interesting.
Yeah. We
So,
want you back.
And this is only week 3. And this is only week 3.
Is it 3 already? I thought it was 2.
Okay, 2. Even worse. He mentioned 4 years of this.
We want you back.
Medicine, schizophrenic medications or stuff.
Report test.
Right.
Yeah.
Yeah, it's interesting what's going on right now. So decision trees basically follow a hierarchical approach, and it's really quite simple to understand. And like once we walk through an example, I think it is quite trivial. However, like actually, like we tried to implement it last year in class, and I realized that like writing these recursive functions is not the easiest thing in the world. But we'll try to get to a point where you understand what's going on, and then like there are many different versions of these, but we'll talk about the basic idea. They can be used for classification and regression, and like I think being able to use them is probably good enough in contrast to like being able to implement them, because they're, yeah, like I understand that like programming recursively is not the easiest task, and especially we did it in MATLAB, and especially in MATLAB it's not trivial at all, and MATLAB actually is pretty stupid about recursion. And yeah, so that was not smart. I didn't think through the homework. Okay, so the decision tree basically tries to do the following. So at the root, which in computer science is always at the top, you have all your data points, and you're making a decision in the top. So that's why it's called decision tree, right? Like you're trying to make a decision, and you try to make a smart decision here, right? Like you could say, if I want to classify, I don't know, family cars or whatever, I would want to say, okay, is engine power greater than 120 horsepower, right? And you would say yes or no, and you would go down a step. So you split up your data set. Then you check, is this new split of my data set unique? Like, are there only one type of class in there, or are there multiple classes in here? And if there are multiple classes in here, I might want to split again, so you recursively split, and basically looks like this. You have two different types of nodes. You have decision nodes where you make a decision yes or no, and you have leave nodes where basically a leave node is you stop at this point, and depending on the class that is dominant in the leave node, and you end up for a new item in this leave node, you would just choose the dominant class in that one. Okay. So yeah, each decision node implements a test function, like that gives you a binary decision. It doesn't have to be binary. Many possible models of decision trees. You could have multiple decisions there too, but let's reduce it to binary for now. And once a leaf node is reached, we would just then basically set the output. Okay, so we have these functions that are happening at these decision nodes. We have the decisions that we're making, yes or no here, and based off of like the class label that each of these leaf nodes get, we make a decision. Okay. These decision trees are also non-parametric, as we don't know any a priori how this tree will look like. We don't define how the tree should be shaped. We have a few parameters that we can set. We can, for example, set the depth of the tree. We can set the type of questions that are allowed to ask, like plus, minus, or like yes, no, greater, equal, and so on. And actually one of the interesting things about this non-parametric method as well is you can make decision trees that deal with any kind of data. So you can build a decision tree that mixes like continuous data with ordinal data with nominal data, and you can make this decision tree however which way you want. So they can mix and match different types of data, because every single node is separate from everything else, right? You just make decisions in each node, and recursively you decide where you end up. So let's look at an example. So for example here, we would choose as the first decision is x1 greater than w10, which is down here. So x greater than w10, x1 greater than w10, so it's like basically sends everything that's here on that side and everything that's here on the other side. And you can already see, well, if we do that, we split off all this chunk here, and we have a clean leaf node here, and everything is circles, so we would make that decision a circle, and then we add a second decision, basically everything that goes up there and everything that goes down here go on different sides, and we have another clean decision for that decision tree. Now, the real difficulty obviously comes from the thresholds and the decisions that you're going to make. So what we need to define, and we're going to, I think, mostly going to talk about this next week, or Wednesday actually, is basically we want to make the best decisions so that the tree is most compact and it has a nice split. So we don't necessarily want to have the threshold right here because we want a little bit of margin again. But also we want to make the decisions that are leading to the the most homogeneous data splits possible. And we're going to talk about this so there are considerations about entropy in your leaf nodes. And you want to choose the one decision that minimizes your entropy and kind of increases the homogeneity of your data set in each of those nodes, so that you can make the right decisions. So a few facts. Each of these decision functions defines a discriminant in the d-dimensional input space, divides it into smaller subregions with ever smaller regions from the root down to the leaves. So we make new decisions over and over again, and in our basic decision trees, we're always only choosing one dimension to make a decision on. Okay, so we have if we have a 20-dimensional input vector, for each decision in each node we would only pick one dimension. Okay, you can build more complex ones where you have if x1 greater than one threshold and x2 smaller than another threshold, you can mix and match, but we're gonna restrict it to these one-dimensional ones. So does anybody know what the difference would be if we could have two variables in the first decision node? Well, instead of lines that go perpendicular to the dimensions, we could come up with diagonals. So we could split it right away with one line, but we're not doing this for now. We're just choosing one dimension at a time. Okay. Yeah, it's just a limitation. It doesn't really need to be like that. You can even have neural networks and more complex classifiers in each of those decisions. So it's really very flexible. Each decision function can be literally anything. So it could, but most of the time it's a simple function, and each tree can be quite complex, but we want to only make small divide and conquer decisions at each point. And so each leaf node defines a local region with a label, and the label is basically just the number or the prior probability for one class over the other class in that small region. Right, so if you have a lot of circles in one region, you would say this leaf node is rather a circle rather than a square class. But they don't always have to be completely homogeneous. So it's not the case that all the time your leaf node has only one class in it. You can have mixed classes in it. Okay, and that might sometimes be desirable because also trees, because they are, if they grow, can become complex. Also, they can overfit. If you are not careful enough, you can come up with a tree that has one item in each leaf node, and all you're doing is a k-nearest neighbor or a 1 nearest neighbor classifier. Okay, so so you got to be careful with that. We're going to talk about how to do this, and then at the end, once we're learned, we only need log2b decisions, and b is the depth of the the number of regions in the tree, and Another bonus, which I think is really cool, is like the interpretability of trees. You can, from the decision functions, can like derive immediately like what is happening. You can say, okay, this feature here, if larger or smaller than a certain threshold, and this and this, so you can come up with logical functions that are really easy to convey to somebody what's going on, like what the classifier is actually doing. In neural networks, that's not so easy anymore. Okay. All right. I think I'm going to leave it here for now. And
We have a test on Wednesday?
yes.
Oh. Okay.
Yeah.
Okay. Yeah.
What should we say?
Can you just go over a little bit maybe?
Everything until like today. Not
Okay.
not today, but yeah. It's not going to be like super hard. It's just checking if everybody's
Not
reading.
asleep.
Reading. Okay. All right.
So
I got
like
you.
readings and PowerPoint.
Yeah.
Okay.
Yeah.
Like, what is machine learning?
Exactly. That would be a good question.
Yeah. Cool. That is, I know. He says one down.
Yeah, it's only going to be like 20 minutes or so.
Okay.